The emerging roles of CO and lactate in elite endurance sports. CO, or carbon monoxide, what's the deal? The term entered the parlance regarding Pogacar's 2024 Tour. It's interesting because, outside of the macroscale role of CO as a pollutant, there is also a strong cellular signaling role with so-called latent cellular HO1-CO system, offering a pathway of benefit outside of the typical erythropoiesis pathway. Altitude, training stimulus, EPO, etc. This is significant because the erythropoiesis pathway is always subject to concerns regarding overlap of stimulus. Of all the many known beneficial training stimuli that exist, their effects are, for the most part, studied in isolation. As long as a training stimulus works on the same pathway, that is, the erythropoiesis path, there is no guarantee from the individual literature that effects can overlap in any way. As a result, this CO breakthrough really is a breakthrough because of a new proposed mechanism of action on a different body pathway. This is perhaps how CO therapy slipped through the cracks, because we think of it as a gas, and gas-related therapy has existed for some time, but always created effects on the erythropoiesis pathway. Current proposed mechanisms of action have CO working more like a drug, in this case as a signaling molecule active directly in the human quadriceps. This represents the second time that a fairly well-described metabolite has been discovered to have a new signaling role in cell metabolism as it relates to elite endurance sports. Putting the emphasis on the word elite, it was actually ISM who just a few years before had created a great study that showed the role of lactate as a signaling molecule on the mitochondrial substrate. His paper, Assessment of Metabolic Flexibility by Means of Measuring Blood Lactate, was a major breakthrough in sports science because of the way that it overlapped high-quality research from the field of human medicine with the field of sports science. ISM's choice to chart pro-trained athletes against moderately trained and metabolically unwell people created an extremely high-quality study and highlighted the role of lactate as much more than just a metabolic waste product. Many have been made aware of the so-called removal of ISM from the UAE ecosystem. This is no doubt a result of his interviews with GCN, where he certainly overstated his direct role in the implementation of any of Pogacar's training. His role in the literature, however, is undeniable, so a deeper look into his identification of lactate as a signaling molecule is due. The ISM paper emphasizes lactate's role as a signaling molecule with significant implications for metabolic health and performance. Lactate is produced during exercise when glycolysis exceeds mitochondrial oxidative capacity, signaling a shift toward carbohydrate metabolism over fat oxidation. This makes lactate not just a byproduct, but a marker of the body's energy metabolism status. Lactate is also linked to insulin sensitivity. In trained individuals, such as professional athletes, lactate clearance is efficient, preventing it from interfering with insulin signaling. This allows for effective glucose utilization and fat oxidation, supporting metabolic flexibility. In contrast, in individuals with metabolic syndrome, chronic lactate buildup correlates with reduced insulin sensitivity and impaired substrate use, making lactate a maladaptive signal in these conditions. Lactate also plays a role in mitochondrial signaling. It acts as a feedback mechanism to stimulate mitochondrial adaptations like biogenesis, which enhances the capacity to oxidize lactate and fatty acids. This makes lactate a key adaptive signal for endurance training and recovery. Finally, lactate reflects the balance between energy supply and demand. In professional athletes, lactate recycling through the Cori cycle or direct oxidation in mitochondria is highly efficient, serving as both a fuel source and a signal for adaptation. In metabolic syndrome, impaired lactate clearance leads to energy imbalances and metabolic rigidity. Lactate's role is context-dependent, highlighting its importance in both metabolic health and athletic performance optimization. A key moment that this becomes relevant is under circumstances in which lactate influences glycolysis. But how specifically does this happen? How does lactate influence glycolysis during exercise? Lactate is a natural endpoint of glycolysis under anaerobic or high-intensity conditions. While it is part of the Cori cycle, its accumulation can signal shifts in metabolic focus. High lactate levels indicate that the rate of glycolysis exceeds mitochondrial oxidative capacity. As lactate and hydrogen ions accumulate, the pH of the muscle decreases, which can inhibit glycolytic enzymes like phosphofructokinase, PFK. This can slow glycolysis temporarily and encourage a transition to other energy pathways, such as oxidative phosphorylation, if mitochondrial capacity is available. Lactate can be exported out of the muscle cell via monocarboxylate transporters, MCTs, and used by other tissues, for example, the heart or liver, as a fuel source. This reduces its local concentration, allowing glycolysis to continue more efficiently. Feedback regulation. While lactate itself is not an inhibitor, the metabolic conditions associated with its production, for example, high NADH/NAD plus ratio, can regulate glycolysis. For example, high NADH levels can slow glycolytic flux by limiting the availability of NAD+ required for the glyceraldehyde 3-phosphate dehydrogenase step in glycolysis. Lactate is an integral part of energy metabolism and plays a dual role. In the Cori cycle, lactate is transported to the liver, where it is converted back into glucose via gluconeogenesis. This glucose can then re-enter the bloodstream to fuel ongoing activity. As a direct fuel, lactate can also be oxidized directly by tissues like the heart or skeletal muscle with high mitochondrial capacity. This highlights its role as an important energy substrate, not just a waste product. This dual role of lactate alludes to certain training modalities and highlights the importance of skeletal muscle in elite road cycling. One cannot help but wonder, given the extent of the PA's adaptations to exercise, if the majority of lactate is oxidized directly in the deepest parts of the human leg, with the so-called lactate shuttle hypothesis not being relevant to PAs. When skeletal muscle both produces and oxidizes a high percentage of the lactate directly, the term shuttling might not fully apply in its classical sense. The classical lactate shuttle concept emphasizes the transport of lactate from glycolytic, producing fibers, to oxidative, utilizing fibers, potentially across different tissues. For example, skeletal muscle to heart or liver. However, in the case of highly trained professional athletes, a significant portion of lactate oxidation can occur within the same muscle group, blurring the boundaries of the shuttle terminology.